Hello, everyone. Please type yes in the chat if you can hear me well. Okay, but we will start in 5 minutes. Okay, I think it's time to start now. Hello, everyone, and welcome to the 116th free webinar titled Well Productivity, presented by Instructor Engineer Omar Magdi. Engineer Omar is a senior petroleum engineer in Khalda Petroleum Company. He has a Masters of Petroleum Engineering from SOAS University, He studies in machine learning and data analysis in petroleum industry. He published a scientific paper titled Prediction of ESP Run Life in Egyptian Western Desert by Machine Learning. He presented many researches like International Field Exploration and Development Conference in China, more than 7 years of oil field experience in production operations, artificial lift system, well intervention, surface facilities, storage, and transportation. Such a great profile, Engineer Omar, and it's a pleasure to have you with us. But before we start our session, I'll just make a small presentation about OPA upcoming service and plan. Here in OPA, we have made more than 55 live courses, which are now converted into recordings and available for sales in different disciplines like reservoir, production, drilling, G&G, and data analysis. So you can scan this QR code to register and check our list of courses. I will also send all the links in the chat, so don't worry if you didn't scan anything. Here is also a feature that we have, or a service that we have in our website, which is OPA App Store. It's like they are like affordable alternatives for the expensive petroleum softwares. They are Excel sheets for specific tasks, and it's all resolved to save time and money. So make sure you check our app store and check the most affordable alternatives for petroleum or oil and gas softwares. Here is one of our best services, which is mentorship. So what's mentorship? It's a one-to-one mentoring sessions by highly experienced mentors. It's like a tailored program based on the mentee's needs. You can request breaks on how to produce output results from a software. You can request us to guide you on personal data of them to get the best output from it, and helping undergrad students in their projects. We have already completed more than 50 mentorship program with more than 950 learning hours, and the mentees were from more than 10 different countries. You can also scan this QR code to register for a mentorship program. Here's our website, opacourses.com, where you can access everything through it, whether you are applying for recorded or live course, enrolling in our free webinars, applying for internship program or for mentorship program or anything, you can access it through our website. So make sure you pay it a visit. And finally, how to be an OPA ambassador. There are two tracks. Take one or more courses with us, or just take a mentorship program. So what will you get from being an OPA ambassador? You will get discounts on all courses in the future, group discounts when you get your colleagues with you. Thank you for listening, and now it's time for our session. Engineer Omar, you can start your presentation now.
Okay, thank you. And would like to thank OPA for this opportunity to share some knowledge with members of the industry, either students or graduates or professionals in the oil field. I hope the sound is clear enough for you.
Yes, it's clear, but it would be better if you make it as a slideshow, yeah.
So today we will talk about a very important topic, which is well productivity. And yeah, we will start by laying some foundations for well productivity, and we will discuss well poor performance and IPR correlations. Finally, I will present some special cases in the oil field, which is advanced or more complicated cases in the oil field. First of all, let's start uh, to uh, to talk about some driving mechanism in the reservoirs. Well, actually, as you know, that reservoirs are not created equal. The driving mechanism affects productivity significantly. If you have a water drive, your problems will be less than you have a solution gas because your pressure will not drop as quickly or as significant as you would expect. Also, the type of wells you have. If you have an oil well, or if you have a gas well, or some problems will arise from gas condensate if you have this operation. It's all like classifications. People try to classify everything so we can use the right tool, the right equation, or the right model to decide what to do or what to expect from your. Also, one of the more important thing in productivity to know the flow geometry of your well. One of the basics geometry that was created from, or we have it in all type of wells, that's radial, horizontal, which we can find in vertical non-fractured reservoir, which the very traditional well system. Also, you have a horizontal linear, which you can expect in hydraulically fractured wells, which now are very common. 20 years ago, 30 years ago, this will be an unconventional type or a new. But now it's very common, very standard practice in some companies to fracture every well, sometimes every layer. So it is now more accessible by companies, so it's more common. Finally, you have vertical radials when you have a horizontal well that is drilled in a reservoir, maybe a tight reservoir, maybe has a small pay zone. So we go to the horizontal well, so the vertical radial well uh, will be present there. Also, how to identify this? Simply, if you have a well testing, a very good well testing and very good data acquisition system, you will know that your reservoir or your well is producing which in which geometry. This is very important, very critical because depend on the geometry you choose, you will choose the model and you will get the results. Maybe some results will be inaccurate because you choose the wrong system. So it's very critical to identify the geometry of the well. So after this foundation, let's talk about definition. We have the well productivity, that's the well ability to deliver oil or gas or both to the wellhead. So well productivity depends on the reservoir and the completion you have, the system, the vertical lift performance you have, VLP and IPR, both together. Another term is reservoir deliverability, which IPR. It depends only on the reservoir performance. That's not so. If you have a reservoir that can produce 1,000 barrels, but your VLP doesn't have this capacity, your productivity will be less than the reservoir deliverability. But if you have a system that can produce 10,000 or the completion can withstand 10,000 barrels per day, and your reservoir doesn't supply only 5,000, so your well productivity is 5,000. So it comes to this question, which is higher. Well productivity will be equal or less than reservoir deliverability. So the application of well productivity analysis or well productivity, studying well productivity is the design of a completion and production system. So you can make sure that your completion system always can hold the amount of reservoir delivered to it. You can also use it to forecast future production and evaluate design and simulation. You have to understand, you have to forecast if you make a simulation system, simulation process you will get and how much. Productivity is the base. for nodal analysis of wells and production system of all time. Also, you will study the any possible or proposed modification, either to the reservoir or to the system, vertical lift system. So, in simple words, well productivity will give you the answer to the most important question in the oil industry: how much oil or gas I can produce, how much oil and gas I can have in the future, next year, after 5 years, after some modification, some stimulation. Do I drill horizontal well or vertical well? Do I do frac or I don't? So the oil industry always revolves about this question. The geology man or the geologist always will have the same question: how much oil and gas in the reservoir? And as a production engineer, for how much I can produce from this well? Do I need another well? Do I need another technique? So it's the simple question of how much I can produce from the well. Reservoir deliverability always depends on Darcy equation. So it's a very simple but very efficient way to understand the fluid flow within the reservoir and the well. It's very common. I don't think anyone in the oil industry doesn't understand it, or at least had a look on this. So that's the flow rate, or the flow of the reservoir, is directly proportional to permeability, and inversely proportional to viscosity, and directly proportional to the pressure gradient, either in, as we can see here, in the x direction, which is the linear, or in a radial system. In the radial system, which is as you said, the radial system is very common in vertical wells, and it's the conventional way of producing oil and gas. You can start by this equation, and you can expand the area to be 2 pi r by h, where h is the thickness of the reservoir, r is the radius of investigation, as we say, or radius of the reservoir. We start from RW, which is the well radius, RE, which is the drainage radius, or the reservoir radius in this case. After some modifications to this constant, is basically we can convert all these units to field units. And finally, we have the term which is important, is the uh, pressure gradient in the R direction or in the radial direction. We can change also the Q to be in the stock tank instead of the reservoir barrel. So we can multiply this by the stock tank barrel by beta O, which is formation volume factor. And by separating variables and some basic mathematics, we can get to the final form, which is a very common, and it is basic of all other models you can see in well productivity, as you can see. It's very simple, very neat equation. It finds that the Q, which is the flow rate, is affected by permeability and the reservoir and the pressure. And we'll talk about this more in a few minutes. But system, it's different. We can expect the gas to behave like an oil, like an water. It both fluids, but they're always different because the properties of the gas is different with pressure and temperature. Because it's not an ideal gas, we have a deviation factor, which is very common in. If you study chemistry, you know that the ideal gas doesn't exist. And in high pressure, high temperature, these properties of gas changes rapidly, dramatically. You can't take it as an oil system, which is we can consider it constant. We start with the same equation, and the beta G here is not constant. It's a function of Z and temperature and P, which is deviation factor, temperature, and pressure. Finally, when we substitute in the original equation, we will get this uh, equation, which is very neat, but there is a problem. Deviation factor is affected by pressure, and the pressure here is present as a function. So Z is a function of pressure and temperature. So we can take separation of variable. Finally, we will take this and we will see there is a function in the integral that's not easily or not radially uh, uh, evaluated. Finally, we will do this and we will make this the MP or the pressure function that is we use. It looks neat, but evaluating the function of pressure, which 2P over mu gz, is not very easy. It's not done, and sometimes it does. It's solved analytically, which is very hard question to answer. And sometimes approximation methods are used, which is very common. And we have several approximation methods to use, especially in different pressure ranges. But you have to understand what I need to know for now in gas systems, that gas system difference because the properties of gas is evaluated in each step of the way and it's not can be averaged easily or can be take as constant as an oil system. So how to measure productivity? With a very simple way to measure productivity of a well is the reservoir or the reservoir density, sorry, the reservoir ability to flow 1 barrel per day per pressure drop of 1 psi. If you drop pressure in the BWF or in the well bore by 1 psi, how much oil you will get from the reservoir, which is productivity. You can see from the previous equation that's Q over delta B. Q over delta B is converted to this very simple equation. This is the basic of deriving or calculating productivity index. You can see it's very simple, but it's not. How? You have K, you have H, you have mu, you have beta O. This is terms are not easily calculated or not easily obtained in the oil field. And you will see why now. So it's very simple equation, but it's very hard to get this data from the oil field. Also, one important topic you have to understand the flow regime of the system you have. You have three: steady state, unsteady state, and pseudo or semi-steady state. First, steady state happens when the pressure drop in the reservoir is zero in any point. When you take any point in the reservoir, the pressure there will stay constant with time. So this steady state flow is very good, but it's not common because it always it's found in reservoirs that have a very strong aquifer or water drive system, which we started to talk about. The driving mechanism is important. The second one, unsteady state reservoir, which is a function. The pressure change with time is a function of the place and time. So if you take a place or a certain point in the reservoir and you measure pressure in this particular point, it will change with time as a function. Finally, the pseudo-steady state, if you take the same point and you start measuring, it will change. The pressure will drop, but with a constant rate. So if you have the pressure drop with time in a certain point equals zero in a steady state, if it's a function of the time, it's unsteady state. The steady state has a constant change. The steady state or unsteady state always prevails in the first period of starting production. It's called the disturbance or starting to disturb the system of the reservoir, which is very important regime. Why? As you can see, this equations is modified for every flow regimes we have. Unsteady state have time, have K, have everything. So the unsteady state is the basic or the starting point of well testing to get information about your reservoir and your well. So it's very important because it gives you insights and the quality of the data you get from this period of production, it will give you everything you need if you do it. But if you don't, you will get the incorrect permeability, sorry, you will get incorrect storage factor and the radius of investigation, and you will get another incorrect data and calculation after that. So you will predict the production wrongly. The general form for oil and gas, as we can see here, what we added the area of the reservoir and the shape factor or the coefficient for this shape factor for the reservoir. How to use it? Some investigators or researchers did this and give you CA or shape factor for every type of reservoir, for every type place of the well in the reservoir, so you can use it with some general form. Doesn't uh, restrict you to the the very first one, which is a radial reservoir and very simple one. No, you can now have any type of reservoir you can encounter, and you will do it. You calculate productivity easily. So after all, let's talk about factors that affect productivity of the well or well uh, reservoir deliverable. First of all, you have reservoir. The reservoir pressure. It's a strong aquifer. It's a solution gas. It's a gas cap. It's a combination. The reservoir pressure or average reservoir pressure is important. Also, the basiness. How much of the reservoir is exposed to production? 1 foot, 2 foot, 10, 100. It affects the production of the well. Also, and the most important one, in my opinion, is the effective permeability. Is the oil can flow through this reservoir or not? If it doesn't flow, you can get it. Even if you have 10,000 million barrels of oil in the reservoir, you can get it. You have to you work around this. Also, the reservoir fluid properties, the beta O and mu O, the viscosity of this oil or gas you produce it. Finally, the reservoir boundary. Is this reservoir huge or it is tight, it's small? The radius of the well bore also affects the production because as you increase well bore radius, you will increase the surface exposed to reservoir and you will increase your production. Finally, near well bore scan. Is the reservoir damaged near to your well or not? If it's damaged, it will decrease. If it's improved, you will increase the production. So any tiny change in the system will affect the productivity, sometimes dramatically. One perforation job that is not done correctly, it will affect the productivity forever. unless you do something. So you have to understand what happened to your well, what it's going to happen when you design something new. This is what you can encounter or you understand in fluid properties. Solution gas is how much gas dissolved in oil, and the deviation factor of gas, the oil formation factor, and the gas formation factor, and other properties. How to obtain these properties? You have two ways. Either you take a sample of this oil or this gas and you do it in the laboratory, which very expensive, and it's not done every week or every 2 weeks, or it does rarely in some oil fields. So you have to take the other path, which is empirical correlations. You have to be very careful to choose the correct correlation for each one and for the range of the data you have. And you do history match and you do matching, BVT data matching to choose the right correlation for your case, because not every correlation works fine for you. Even it is a good correlation, but it doesn't work for you. So you have to be very careful to choose the right correlation before you start. How to choose? This is another topic, and this is very complicated question, but experience will get you there and guidance through some softwares and some papers will you can find the right path for you to start. So type of the rock, it's found easily from sampling. Porosity, it can get from core samples and from open hole logs, which is very easy. Sometimes it's very easy to obtain in the oil fields, especially in the first days of the well when you are drilling the reservoir for the first time. Permeability, as I told you, is very important and very tricky because it changes rapidly. You can take it from well testing or from some sampling, but it always comes from well testing because it changes with as you produce some oil, some water, some gas, the effective permeability of each component will change. So you have to redo the testing and you have to readjust your calculation every time because permeability, absolute permeability of the rock is like if you don't do any stimulation, it will be constant. But the relative permeability and the effective permeability will change as the saturation of each component changes. Okay, skin factor, it's the damage or the alteration, for more general term, is the alteration around the well bore. Uh, it has several components, combine them, and you have the total skin factor. First one is formation plugging. While the formation is plugged, scale, precipitation, salt sometimes, uh, mud, mud fluid that done some damage to the formation around the well bore. Second term, theta is partial completion and diffusion angle. If you penetrate the reservoir with some angle, it will affect the productivity, and it can have a good influence or bad influence on productivity. Partial completion is when you don't perforate all the way. You'd only have some portion of your reservoir is completed with the perforation, or you plug some of the reservoir and others is open to flow. Maybe you can do it in purpose, or you do it by mistake or by operation that's not intended to do. Now, the ideal flow condition near the perforation is when you have high flow rate gases. Sometimes non-ideal flow conditions near the perforations when you have high flow rate of gases that create disturbance around the well bore and reduces productivity. Also, the dark effect, which is also related to gases. So the question is, can we remove this effect? Yes, certainly yes. You can remove the formation plugging. Maybe you can remove this partial compression by redoing the perforation or reopen the whole thickness of the reservoir. Maybe. But if you have a lesion in your well bore, it's very hard, maybe impossible. Also here, you can adjust this by choking and by other means to reduce the 9 IDF. Here, it's not because it's related to gases, and when you flow gases near the well bore, Darcy effect will be always present. So sometimes you can remove the skin factor or enhance the conditions around the well bore, and sometimes you don't. How to remove formation plugging? The first one, which is the important one, we always do some treatment by acidizing, by fracturing, a lot of a lot of stimulations intended only to remove this plugin. Multi-phase flow. You don't always produce the same fluid from one well bore. You will produce oil, you will release water, and you will produce gas. Sometimes all of them together, sometimes only oil and gas, sometimes gas and water. It depends. If it's a gas reservoir, it's an oil reservoir. But let's say all you will have water flow with your petroleum product, either oil or how to calculate? Very simple. The same equation you have, but you will change one thing. You will do the effective permeability of each component. How to do it? You multiply the relative permeability of oil with the permeability of the reservoir, which is the absolute permeability. And so on, you have the effective permeability of the oil. So on with water and gas. How to get this? The relative permeability uh, curves are sometimes found in some softwares, and sometimes you produce them for your reservoir by testing in the laboratory. So it's there. It's not hard to obtain, or it's not possible to obtain. It's already uh, there, and you can predict the behavior of oil and water. Depends on the situation. I will do an example about this multi-phase flow later in the presentation. So, but you have to understand when you uh, try to calculate oil flow, you have to use the effective permeability of oil, you have to use the effective permeability of water, and you have to use the effective permeability of gas. Fractures well, as I said, it's a common practice in almost every company now uses hydraulic fracturing. The technology is there. It's easy now to do this, and it's very effective way to enhance production. So you understand what are you doing with fracturing? We increase conductivity. So you have to calculate the fracture conductivity by this equation. It relates the fracture permeability, width of the fracture, and the length, half length, the fracture, and the matrix or the reservoir permeability. The flow equation is modified. How? The skin factor is the skin factor of the fracture. The skin factor of the fracture is always a negative. So we have a negative term here. It reduces the denominator and will increase the production. So when you have this case, you have an improved productivity index by this term, and you can calculate it. So if you have, when you calculate or you are designing your chip, you will can, in the design process, you can predict the fracture conductivity, so you can predict the skin factor of the fracture, and you can predict how much gain oil or gas you will get from your reservoir, which is a very important question. Because if you don't know how much you will get from this distillation process, you can and you can't evaluate it. Finally, it's a matter of, it's a business. So you have to persuade your managers that simulation is important. How I will get this amount of oil increase, and I will get this amount of gas increase in the first year or the first 2 years, and it's justified or not. Because guess what? Simulation is not cheap and it's not easy. Even the technology is there and it is a standard practice now, but it's not cheap. Nothing's cheap in the oil field. So you have to calculate everything, and you be sure several models are there to uh, predict the fracture conductivity, which is another topic, but it's there. You can use it. You can use it by software. You can use it by equations by hand, but sometimes you have to understand how to calculate this and how to evaluate your stimulation process. Okay, how to understand? You ask me how to get the skin factor. The skin factor for fracture can be done by correlations. A very good correlations here by Lee. When the fracture conductivity is over 100, you can use this simple equation, approximate fracture skin factor. If it's under 1, you can use this more complicated correlation. But we have to stop here for a minute. Let's say you have the same fracture, design it, the same conductivity of the fracture, the same length, the same width of the fracture, but in two different reservoirs. One reservoir is very tight, so the Km or the matrix conductivity is very low. So the fracture conductivity factor here will be very, very high. Let's say over 100. Another one is the matrix conductivity is very low. It's very, if it's very high, you will get this number low, fractional conductivity, and you will use this. Another type, when this is very low, the fractional conductivity will be very high, and you will use this. So if you are in a tight reservoir, the factor that affects the skin factor is the length of the fracture. And if you have a very good conductivity in the matrix itself or in the reservoir to begin with, the most important one is the conductivity of the fracture and the width of the fracture. So you have to understand this. If you have a low permeability reservoir, you have to increase fracture length. So you can get a more negative number for the skin factor. But in a high permeability reservoir, you need to increase fracture permeability and width. So you have to do your time for each reservoir. You can't take the same treatment in each reservoir you have in your company or in your field. It's not logic. So in high permeability reservoir, you want to increase the fracture permeability and width. In low permeability reservoir or tight reservoir, you need to understand to increase fracture length. I see someone is having a question. I will answer the questions after
Omar?
the presentation. Okay.
Engineer Omar, can you hear me?
Yes.
I just want to ask that is it recorded?
Yes.
Is the session recorded?
Yes.
Okay, because I'll need a video after the session. That's why I'm asking.
Yes, it's recorded. Our channel on YouTube.
Okay, that's good.
Okay, thank you. Engineer
Thank
Omar,
you.
hello. I'm Tahar from OPA. I'm just
Yes.
telling you that we're losing your voice sometimes. I think this is a bad connection from the internet.
Okay. It's clear now.
Yes, it's clear, but sometimes we're losing it. Okay.
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 If you are losing, please raise your hand so I can understand it's losing. I will
I'm
stop for
already
a minute.
sending private message on Zoom. Okay, تمام. Okay.
Okay.
Thank you.
So let's talk about horizontal wells. Horizontal wells is used in tight reservoirs. It's used in reservoir with small pay thickness, so it's not optimal to use vertical wells. So horizontal wells is also used. Horizontal wells has an effective radius here, called REH. That is the drainage area of this reservoir, this well. Also, the bay thickness. We have a toe. That's the end of the horizontal section. Heel, which is the start of the production or the horizontal section of the well. This is the model or mathematical model for the horizontal wells, as some publications
Engineer Omar, can you hear
suggest.
me?
Yes,
Hello?
yes. Do you hear me or not?
Yes, but now there is no voice.
Now is okay, or there's a problem with the connection?
Yes, it's back. Yes, it's back.
Okay. Sorry for this interruption. I don't know what's the problem. Okay, let's go back to the session, the presentation. So some publications suggest this modification to the flow equations in horizontal systems. You have to understand two things: that it's affected, the horizontal wells are affected by INI, which anisotropy permeability, and the flow coefficient here in the both equations for gas and oil. It's called the flow coefficient sometimes. Okay, anisotropy is the like it's a ratio between the horizontal and vertical permeability. When do you have a very tight vertical permeability or low vertical permeability, it will affect this, and you have to reconsider if you do another stimulation method or something to increase the vertical permeability for your well, because and you have very low vertical permeability, which as we said, in both the direction, it's a vertical radial system. So you have to make sure that your vertical permeability is good and is not too low, so you can allow flow from all the direction to the horizontal section. Another one is the flow coefficient here, which is like some authors don't account for the friction loss in the horizontal section itself. When the oil enters the horizontal section of the well, it flow all the way to the heel, then the vertical section. So this coefficient is also calculated empirically. It gets you this effect in your equation, so the productivity index will be lower because of this fraction loss in the horizontal section. It's published. If you want, can share the method with you later, but it's a little bit complicated. But you have to understand, in the horizontal system, you have to make sure that the vertical permeability is good and it's enough to produce or to justify drilling this well in a horizontal section, and also the flow and the friction within the horizontal section is not too much, so you will lose production from your well. Okay, let's talk about the second part of this is well performance. Well performance is the fluid flow within the single flow in the well bore or the well itself after it leaves the reservoir. So in the first law of thermodynamics, the pressure drop. This is very common, and it's about two things: about the due to the velocity change and the elevation change and the friction. So it's the three terms we have. Single flow, oil or water, it's very not that common because always you have gas in the reservoir. But if you produce even above the bubble point, you will also have oil only or water only in your system, which is a very good system if you have. But I never encountered a well without gases or without stagnant flow type of flow in the well bore. But it's there. Friction, the enemy of fluid flow in the well and in your surface facilities. You always care about friction. The friction is calculated from this term, which fluid uh, related to the viscosity and the velocity and the length of the section that the fluid flow go through, and finally the diameter of the tube you have. You can sometimes, this is a chart you always encounter in thermodynamics and in fluid mechanics. You have to understand that it is used to calculate the friction factor here, and several correlations already are very common, so you can use it to calculate your you can understand this correlation. It depends. Some explicit, some introduced by trial and error, and so on. But you have to understand one thing now, or as a foundation for your understanding for your productivity, is you need that as you decrease the fluid, the tubing diameter, you will increase friction. So a lower diameter will increase friction. This is the case. Oh, but be careful, because there is a sweet point between the well lose all its productivity power when you increase it too much. And if you decrease it too much, you will lose a lot of pressure due to the friction. So you have to understand this, and this is very important to you. And also will change the fluid patterns in the well. Okay, multi-phase flow. We have, let's see, multi-phase flow. We can start by bubble flow, which is all the continuous phase is liquid, and there is a bubble of gases within the continuous flow. On the other end is the opposite. We have mist flow. Mist flow is the continuous phase, is gases, and some you have like droplets or small droplets of liquid. In between, there is slug flow, champ flow, annular flow. We always look for one thing. if you can reduce by bubble flow and mist flow, you have to do it, because it's not only decrease the pressure drop, it also save your pipe. If there is someone in your field is concerned about erosion and erosion, they will always tell you that you have to do mist flow and bubble flow instead of annular flow or slack flow. It's very damaging to the piping. In some cases, when you have multi-phase flow, the fluid build up or liquid hold up should be encountered. Why? Because the more dense or the more that has more dense fluid will travel lower. So you have to understand that not all the disturbance of the liquid gases are the same during the fluid flow through your media. Should be understand and encountered through in your calculation. Liquid holdup can be calculated only experimentally. You can take it in the experiment, but you have to. We can encounter 4, but we're not calculated exactly. So we have to calculate pressure drop this. We have 2 systems: the homogeneous system, which is the old one, that are less accurate, but it's easier to code and construct in a data sheet or something, but it doesn't encounter for, this an example of this type, but doesn't encounter for liquid holdup. Separated flow do this, account for the liquid holdup, but it's always difficult to code in your software or your Excel sheet. So it's very complicated, a little bit complicated. But now some softwares give you this correlations very easy to use. Let's move on for gas. As we can say, as pressure drop, the gas properties will change as we speak before about this, and it will be very difficult to encounter for all these changes. I will go this through a little bit fast for the time. But along your pipe or along your pipe tubing in the well, the temperature change, the pressure change, so the fluid property change, and we have to encounter this. How it's approximated? There's 2 types of solutions: average temperature and compressibility factor, which is used in a certain range of pressure and temperature, and other one is this method, this Callendar and Smith method, which also used an approximation assumption. How you can use it? It's an iteration. It's very difficult to calculate by hand, so you have to do it always by Excel sheets or by software, because it's a very iteration, and you have to divide your the length of the tube into small increments, so you can get a good calculation. One of the more important questions in wet gas production is when you have gas with water or oil, can liquid build up and drop in the tubing and finally shut off your production at all? This is a very common problem in some reservoirs, but it has signs. What signs to diagnose this problem, that you will have a liquid loading in your system? Liquid slugs at the surface. You are producing gas, but you have sometimes a pressure change between casing and the tubing. Sometimes the flow rate is dropped dramatically out of the sudden. What to do is artificially forcing liquid out, and you have using narrower tube also, or have to gas lift or pump the well or increase heat so you can have more gases and to kind of how to understand this liquid loading in your system. We have a very simple method called Turner method. this equation, you can use it to calculate the velocity necessary to hold all the well from your well up to the surface. There is one problem. This method is simple and reliable, but you have to increase the amount of velocity you take here by 20% to be safe, because it tends to underestimate the flow rate required. This is the flow rate required in million cubic feet when you use the velocity or this method called. Finally, one of the most important topics in productivity is the IPR correlation. Why we use correlations for RPR and for well deliverability? Because you don't have all the required data to calculate well productivity by hand. Maybe you don't have enough data for permeability. You don't have the ability to do a well testing, but you have a surface testing facilities. Good enough. And you have shut off the well for a certain time so you can get the static flow, the bottom hole pressure. So you have the reservoir pressure and you have a test point. More than enough for Vogel method. It's very common, it's very effective, and it's very important to understand. Also, you have another correlate called Petkovich equation. Also, if you have the two test points and you okay to go, you will calculate everything you need. So we use it when you have limited data and a simpler method, and you can update every time you get a new surface testing or a test from the oil field from the production supervisor. Okay, we'll go deep a little bit with Vogel method, which is more common and more frequent used in the oil field. This is the IPR curve, as you can see it. Above bubble point, it all produce only oil, so it's a straight line with productivity index as the slope. The increase after the productivity in the productivity after we drop below the bubble point is approximated by this. Finally, you have the general form that can be used either above bubble point and below the bubble point here. So it's all good. So you can have that reduction here in the straight line, and when the BWF or the well bottom hole pressure is above the bubble point, after it decreases under the bubble point, you will have another increase by this amount. From test point, if it's single phase oil only or partial two phase, you have this. You can use it to calculate the productivity index here in single phase. In partial two phases, if it is increase, the pressure drop is below bubble point, but you have the test point above the bubble point, you will use the same equation. If the bottom hole pressure below the bubble point, you will use the general form of this to find the productivity index. Also, for saturated reservoir, when you use it to you always produce oil and gas, so this Qmax will be used to estimate the Qmax of the or the open hole flow of the well from one test point, as you can see here, and you can finally find the productivity index and so on. Sometimes you don't, or most of the times, you don't only produce oil, you will produce oil and water. So there is a correlation for this. When you reduce 100% oil, it's a straight line. And this deviates until you get 100% oil here. And in between, you can between these 2 points, from water cut from 100% to 100%, you can get sorry, you can get this data. It's also trial and error method. It's very complicated a little bit in especially in hand. So some softwares get the alternative, which this relative permeability curves that already exist in some softwares like Prosper. They use it to find the saturation. You say I have 100%, 50% water, so they get the relative permeability of oil, then calculate the total mobility of this test point, and finally to get a new productivity index, or J as we can find it, you multiply the old mobility ratio, by the old productivity index to get the new productivity index for each for this test, and you construct IPR. This method is not easy to use, but it's found in some softwares like Prosper, so it's very common, and you need to understand it that it's used by, if you have a water cut, get the relative permeability of oil and the relative permeability of water, and you finally get viscosity and formation volume factor for water and oil from correlations, and then calculate the mobility and adjust the PR. Finally, we can talk something about composite IPR. When you produce from several layers at once in the same well pool. I will not go in much details here because of the time, but let's say you have several. One, you assume that all the fluid comes from this layers are the same, and the pressure loss in the well pore sections are negligible between the layers, not in the whole well pore, but between the layers, and the IPR of individual layers are known. So you get a summation of the fluid flow coming out of the wellhead is the summation of each individual layer, and so on. So when it is a single phase only oil, you can get this. When two-phase flow, when you have gas and oil, like a saturation reservoir, and saturation reservoir, yes, here, and you will get this like from Vogel correlations also. You can calculate the open hole flow for all the layers together, and for the fluid, the flow rate for all the layers together. One thing to understand here when you do it, that when you calculate pressure, you have to get a data point. What's a data point? You calculate all the pressures to a certain point or a certain depth in the well. So you can choose a data point. So all pressures are related together, not each pressure, because this will not make any sense to calculate pressure for each layer in its place. No, you can convert it to a data point, so all things hold up. This is also for partial two-phase flow. Finally, you have this individual IPR. This is an example from a textbook. You can see that every layer is known here, the IPR. Finally, the composite IPR is here. And this is a comparison of the data. When we decrease bottom hole pressure, we find the commingle of the all layers production, and each layers have some production. You have to understand that's not always the case, that you have the all layers production is equal to the summation of each layer production. Why? Because there is a cross flow between some layers. The cross flow, that one oil, certain data, certain layer will get oil out and goes to the another layer. How to prediction of future ITR, as we told, if you do a stimulation or something in the well that affects productivity, you have a Vettel method that gives the ratio between the future and the present properties of the reservoir, which is the mobility ratio of this, or the future and present ratio of permeability and the formation volume factor. Perkovich method simply have a similar, but it only gets the ratio between pressure present and the reservoir pressure in the future. So it's a good method to predict the future of the well after depletion or after stimulation. This is the reservoir at 2,250 psi, and this and at 1,800 psi, and this is predicted by Vogel method. It's a very common method to use to predict this. Let's talk about some special cases. Finally, and this will be the last part. I will go through it quickly because it's very complicated and it needs more time. But I will give you some insights about it. So multilateral wells, we have to, it's a well that has multiple branches from a main borehole. We have two types of this material fishbone. When you drill a horizontal main well bore and drill laterals or branches from this horizontal well. It's used in tight reservoirs that has a vast area that can be reached by one horizontal well bore. Another type is root well. The main bore is vertical and the laterals or the branches are horizontal to reach two different pay zones. You have a different pay zones. You need to minimize cost by not drilling in an individual well for each well. You can use root wells. Fishbone wells, this is the main well bore here, and these are the laterals. The distance between each lateral calls 2YE, and this radius is the drilled area, as we can see. The initial fluid flow is pseudo-linear. Then finally, the pseudo-radial flow may prevail later drainage if the drainage area outside the drilled area is very large. So you have two systems. One in the inner region, which is the drilled area as we see in the circle. It's defined by this. It's almost near to the, what we can say, the horizontal well. And the other one is outside the drilled area, which is radial system. And this, if you can combine the two equations together, because the fluid flow comes from the outer area, is the same flow that enters the inner area that finally goes to the well, you will get this equations, and you have to understand what affects the fishbone model. It affects by the shape factor of the all the drainage area of the reservoir, and also affected by the individual distance between laterals and the isotropy as any horizontal well. As I said, that's the vertical permeability should be not too tight in this type of wells. Root wells, it's very complicated a little bit from the other one, and it's not that common because you reach different strata at the same time, and the calculation is not very easy because it depends on trial and error. How you start by assuming a fluid flow, a certain amount of flow from the wellhead, and you start to calculate the pressure drop until the first lateral. Then you construct IPR depending on this pressure here, and then you continue VLP to the lateral and so on until you reach the last branch, and finally you get this. If it is holds and you the constructed data is holds with you, you will find your answer. But if it's not, you will change your assumptions and so on. So it's a time consuming and it's very a little bit complicated, but it can be done with some help of software. So trial and error approach, as I told you, you combine the inflow and outflow analysis for each lateral until you get your answer. We talked about this, we don't have to repeat ourselves. Okay. Another type of well is multi-fair horizontal wells. When you have a horizontal well, but you do fractures or multi-stage fracture. Why we use this type? We use it in unconventional reservoirs like shale, right? Very tight sand or so on. Also, it's very common. It's very similar to this to horizontal well or fish wells, but it's fractures, not laterals, not branches of this well. What's different? Because there is a little bit more regime. We have a radial flow, we have a linear flow, and we have the radial and linear and inner linear within the fracture itself. So the calculation method starts by reservoir radial flow within the drainage boundary to the fracture region or the drilled region, and the linear flow between fractures in the reservoir, and fracture linear flow in fracture to the near bore. So not like the other one, the fishbone, it has two components. No, here it has three components of this system. Finally, combining all equations, as we see, that's all the same. We have this type. What affects this type of well is the fracture half length, the distance between fractures or the stages of the fracture, finally the width of the fracture and the fracture mobility itself. So I think I'm done today. I'm sorry I take a little bit long than scheduled, but I hope this presentation was insightful for you and give you basics for what you need to know about production engineering and well productivity. It's a very big topic, and I hope I give you some insights about it. And now I will leave the floor for the academy people to get any Q&A. And I hope you enjoyed the session, and thank you for listening.
Thank you, Dr. Engineer Omar, for this fruitful and great session. Thank you for your effort. Now it's time to receive attendees' questions, and please write your question in the chat box. And we will take 2 minutes break for the feedback form, okay? Already, I will send it on the chat box. hope to fill it now. Please visit our website to bring, the website to the certificate will generate it automatically tomorrow, inshallah. If you have any question, please put it in the chat box. No questions? Engineer Omar, I think there is no questions. Thank you for your time and your effort.
Great,
see
Staha.
you, inshallah, in the next webinar.
Inshallah, thank you for your times, everyone. I would like to urge you, if you have any questions in the upcoming days, you are free to contact me by email, by LinkedIn. I will be more than happy to assist you with anything. And I would like to thank OPA for this opportunity, for this
Thank
amazing
you.
opportunity.
Thank you, Engineer
And
Omar.
I hope we will see you soon
Our
in another webinar or another course. Inshallah.
Thank you. Inshallah. Thank you. Thank you all for
Thank you.
attending this webinar.
Thank you.
Bye-bye.